Imagine this. You're thinking about a new app screen, maybe a complex dashboard, or perhaps a really slick e-commerce interface. You just described it, in plain English. And bam, an AI instantly generates not just a picture, but actual working compiling code for that UI. That's the kind of future we're diving into today. We're unpacking a really fascinating paper, UICoder, fine-tuning large language models to generate user interface code through automated feedback. Okay, let's get into it. The core problem this paper tackles, it's a huge headache for any developer. UI code, that's the bit users actually see and touch, right? And it's notoriously tricky, incredibly time-consuming to get right. Often makes up like half of an application. Now, large language models, LLMs, they show amazing promise for code generation, yeah? But they've really struggled, to consistently produce UI code that one, compiles, and two, actually looks good and works properly. And the ways people tried before usually involved super expensive human feedback slow, costs a fortune, or maybe distilling knowledge from big proprietary models. But those often come with restrictions.
Neither is really ideal. So our mission in this deep dive is to explore how automated feedback, and we mean fully automated, no humans needed in the loop there, how that can guide LLMs to become incredibly good UI code generators. You're about to get a shortcut to understanding this really innovative approach. And trust me, it's pretty transformative.
Yeah, it really is. And what's so fascinating is just how hard UI generation is for these LLMs. Even with all the data they've seen, you'd think mountains of text, mountains of code, they'd nail it. But the UI code, it's a different beast. Examples of really high quality self-contained UI code are actually surprisingly rare in general web data, like sometimes less than 1% of the training data sets. It's a scarcity problem. Plus, you've got UI toolkits like Apple SwiftUI, which use a very particular programming style.
Okay, when you say particular style, what exactly makes SwiftUI so tricky for an LLM that's seen tons of other code?
Well, it uses what we call functional and reactive conventions. Think of it less like a step-by-step recipe and more like describing the final dish and how the ingredients react to each other. You describe the state you want your UI to be in based on the data, and the framework figures out how to make it happen when the data changes. It's a different way of thinking, a different paradigm compared to the more common imperative code, do this, then do that LLMs see most often. It's almost like learning different sentence structures entirely.
That makes a lot of sense. That distinction is key. So given those hurdles, the previous attempts, they often hit major roadblocks, didn't they?
Absolutely. The traditional ways, like you said, either needed costly human feedback loops labeling, rating, which is just slow and doesn't scale well, or they tried distilling from the big proprietary models, like, say, GPT-4. But while you might get a downloadable model out of that, it often inherits usage restrictions, maybe non-commercial use only. And fundamentally, it's capped by how good the original teacher model was. You're not really breaking new ground, just getting a potentially limited copy.
Right. That really paints a picture of the limitations. So faced with all that, what was the sort of breakthrough idea from the UICoder team? How do they get past these issues?
The big idea, the real breakthrough, was this concept of an entirely automated, iterative self-improvement cycle. They basically cut out the need for expensive human labor and avoided the restrictions of proprietary models by getting the LLM to essentially teach itself, like an AI becoming its own coding coach.
That's the heart of it.
Yeah.
So how does this self-teaching thing actually work? Can you give us the overview?
Sure. So it starts with an existing LLM. They use StarChat beta in the paper. They prompt this base model to generate a huge amount of synthetic UI code based on natural language descriptions. Just churn it out. But here's the really smart bit. Automated tools, think compilers, other AI models like vision models, then step in to rigorously filter, score, and deduplicate all that generated code. This creates a much smaller but much higher quality refined data set. And then the original LLM gets fine-tuned on this new high-quality data set that it helped create. This makes the LLM better, so in the next round it generates even better data. It's this virtuous cycle, an AI coding bootcamp refining itself each time.
And they focus specifically on SwiftUI for this work, right? Apple's framework for building UIs across Mac, iPhone, iPad.
Exactly. They needed a concrete target. But the core method, this automated feedback loop, it's designed to be general. You could, in theory, apply it to Flutter, React Native, maybe even web frameworks. The process is the key innovation, not just the SwiftUI result.
Okay, that's crucial. So to really get how impressive this is, let's dive into the mechanics of that self-improvement loop. They started with, what I'd call an underdog model, StarChat Beta. It's a 15 billion parameter model, fully open source, which is great. But here's the wild part. StarChat Beta had almost zero Swift or SwiftUI code in its training data. Like none. Apparently, Swift repositories were accidentally left out of its training mix, and there was only one Swift example in like 10,000 instruction tuning examples. Basically nothing. So its ability to generate UI code initially, predictably very, very poor. It was starting from way behind.
It really was, which makes the final results even more striking, right? It shows the power of this self-correction approach. So, to kick things off, they needed input descriptions linked to UI examples. They gathered UI screenshots from various datasets. For some datasets that just had images, they used a visual language model, a VLM, to generate some basic descriptions, weak labels, they called them. For others that had simple human descriptions, they used another LLM to kind of flesh them out, paraphrase them, add more detail. But crucially, to stop that second LLM from just making stuff up, hallucinating details, they used a VLM again to check the enhanced descriptions against the original screenshots, a quality control step right at the start.
Okay, that initial data prep sounds pretty clever, setting the stage. But you mentioned earlier, the real magic, the sort of secret sauce of UICoder, is that automated filtering during the fine-tuning, right? That's where the self-improvement really happens.
Absolutely, that's the engine room. This iterative supervised fine-tuning, which they ran for 5 cycles for the main model, UICoder SFT, relied on 3 absolutely critical automated filters. First, compilation success. Simple binary check. Does the generated Swift code compile using Xcode? Yes or no. If it didn't compile, it was thrown out. This was non-negotiable because the next checks needed code that could actually run and be rendered. And initially, most of it failed this basic test.
Yeah, that makes sense. If it doesn't compile, it's useless as code. What was filter number 2?
Second filter was the CLI score. They used a vision language model, CLIP, to measure how well the rendered screenshot of the generated UI matched the original text description. And they did something clever here, too. They tweaked CLIP slightly to make sure it wasn't just, finding the prompt text in the image and giving a high score. It had to actually assess the visual layout's relevance to the description. Avoided a simple cheat.
Ah, smart, ensuring genuine visual understanding. And the third filter?
Third was deduplication. You don't want your model just learning slight variations of the same UI over and over. That leads to poor generalization. So they used a clustering algorithm. It grouped visually similar UIs together based on their CLIP embeddings, essentially, their visual fingerprint. Then, from each cluster, they only kept the single best example, the one with the highest CLIP score. This ensured the training data was diverse and high quality, preventing dataset imbalance.
Wow, okay. Compilation check, visual relevance check, and diversity check. All automated. So starting from that StarChat beta model with almost no SwiftUI knowledge, after applying these filters in the first round, what percentage of the generated code actually made the cut?
Get this. Initially, the proportion of high-quality examples passing all those filters was a minuscule 0.4%, less than 0.5%.
0.4%. That's
Very
tiny.
tiny. You'd probably give up, right? But here's where the iterative magic happens. With each round of fine-tuning on that tiny sliver of good data, the model got better, significantly better. In the next cycle, it generated a higher percentage of code that passed the filters, and that better data was used for the next round of training. The paper has these graphs, figure 2, showing compilation rate and CLIP score climbing steadily over the iterations. It's a really dramatic visualization of the model pulling itself up by its bootstraps.
That's incredible, going from almost nothing to progressively better results purely through automated self-correction. But hang on. After those 5 core supervised fine-tuning cycles, they also did something called preference alignment for some models. What was that about?
Yeah, that was an additional refinement step for some variants. After the main SFT stage, they'd have the improved model generate multiple possible UI code outputs for a single description, maybe 10 different versions. Then, these versions were ranked automatically. Compilable code always came first. Among the compilable ones, they were ranked by their CLIP score, visual relevance. If code didn't compile, it was ranked lower, based on the proportion of lines that were error-free, a sort of partial credit system. This process led to 3 slightly different final models: UICoder DPO, UICoder Top, and UICoder Filtered. It was about exploring different ways to leverage preference signals, even automatically generated ones.
Right. And running this whole complex cycle, generating code, rendering UIs, running checks, retraining, that must have required some serious hardware, right?
Yeah.
What did the infrastructure look like?
Oh yeah, this wasn't running on a laptop. They needed dedicated infrastructure. We're talking code generation happening on powerful V100 and A100 GPUs. Then, separate UI renderers, basically macOS machines running Xcode and iOS simulators just to turn the SwiftUI code into screenshots for the CLIP evaluation. And of course, training servers for the fine-tuning itself. They even implemented some lightweight automated program repairs using regular expressions, little fixes for common, simple errors before even trying to compile, just to improve efficiency. It shows the level of engineering needed to make this whole automated loop hum.
Definitely a sophisticated setup. Okay, so they built this impressive self-improving system, took an underdog model and turned it into something powerful. The big question, how did it actually perform against other models? The competition.
Right, the evaluation. They put together a custom test set, 200 diverse UI descriptions, manually checked, averaging about 20 visual elements per screen, pretty decent complexity, and they measured performance using three main things. First, compilation success rate, straightforward, does it compile in Xcode 14? Second, the CLAP score, using that improved version to check visual relevance against the description. And third, human preference ELO. This is interesting. They had 6 human-computer interaction experts from their own team-rate pairs of UIs generated by different models without knowing which model made which UI. These pairwise wins and losses were converted into an ELO rating like you see in chess rankings.
Okay, blind human ratings, compilation, visual score. Seems thorough. And the results. You mentioned StarChat beta started at the bottom.
It was a total transformation. The UICoder models didn't just get better, they dramatically outperformed all the other downloadable open-source baseline models they tested against. And even more impressively, they started approaching the performance levels of much larger proprietary models like GPT-4. Remember StarChat beta? Initially ranked dead last after the UICoder training, it shot up to become one of the top performers. 0 to hero, basically. It's a powerful demonstration of the method.
That really is remarkable. Any surprises when they look closely at how UICoder compared to the other big names, like the GPT models?
Yeah, a couple of things stood out. One slightly counterintuitive finding was that GPT 3.5 Turbo actually had a higher compilation rate than GPT-4. The researchers guessed that maybe GPT-4, being more capable, was trying to generate more complex, ambitious UI code, which naturally increased the chance of introducing subtle compilation errors. Meanwhile, one of the UICoder variants, UICoder Top, actually beat GPT-4 on compilation rate. That's a huge win for an open source-based model. Another interesting point, those different preference alignment variants, DPO, Top, Filtered, didn't end up performing wildly differently from each other. This kind of suggests that the main supervised fine-tuning loop, those 5 cycles with the core filters, did most of the heavy lifting in terms of performance gains. The preference tuning was maybe just icing on the cake.
And the high-quality dataset that UICoder generated through this whole process, could that be useful beyond just improving UICoder itself? Could it help other models?
Yes, absolutely. And that's a really valuable contribution to the community. They show that this high-quality synthetic dataset could be used to fine-tune other LLMs. They took models like MPT-30B++ and MPT-7B++ and fine-tuned them just on UICoder's generated data. And these models showed significant improvements in both compilation rates and CLIP scores. It proves the value of the data itself. Other researchers or developers could potentially use this dataset to improve their own models for UI generation without needing to replicate the entire complex UICoder self-training pipeline. The bigger MPT-30B++ model got the best results from this distillation.
That's great for the open source community. Now, UICoder is clearly a big step forward, but like any research, it's important to talk about the limitations, right? What are the current boundaries or risks?
Definitely. First, scope. The work published focused primarily on SwiftUI. While the method seems generalizable, they haven't explicitly shown it working just as well for, say, Android development with Jetpack Compose, or web UIs with React or Vue. That needs future work to confirm.
Okay, so proving generalization is still needed. What about relying only on synthetic data? You mentioned the upside, but are there downsides?
There can be trade-offs. Purely self-generated data, even when filtered, might lack the sheer breadth and diversity of real-world, human-created examples found in massive web crawls if high-quality UI kit are abundant there, which it isn't. However, the evaluation results suggest that their filtering was strong enough to create a very effective dataset, even if it might theoretically be less diverse than some hypothetical ideal human dataset. The proof is in the performance pudding, really.
Makes sense. What about the feedback signals themselves? Like the compiler just says pass or fail. Is that maybe too simple?
That's a great point. The binary pass-fail feedback from the SwiftUI is quite blunt. It doesn't tell the model how badly it failed or if it was close. This might inadvertently push the model towards generating simpler code that's less likely to have errors, rather than learning to write complex but correct code. risk aversion, essentially. And remember, they tried ranking non-compiling code by error-free lines. That actually made compilation rates worse. Maybe it encouraged like tiny, trivial code snippets instead of full UIs. Counterintuitive. Similarly, the CLIP score is good for overall visual relevance, but it's not a design expert. It struggles with subtle things, bad alignment, text overflowing its container, maybe accessibility issues, and it only sees static images, missing interactivity issues. It's not perfect visual feedback.
Right. Subtle design flaws or interaction problems might slip through. And the human evaluation. Any caveats there?
Well, the human evaluation relied on static screenshots too, so like CLIP, it might favor UIs that look good over ones that work well or feel intuitive to interact with. Functionality is hard to judge from a picture. Also, while the raters were HCM experts from the team and the process was blind, using only 6 internal raters is a smaller pool than, say, a large-scale user study. It's a practical limitation in research, but worth noting.
And finally, the general risks associated with any powerful LLM.
Absolutely, those still apply. UICoder, like any LLM, could potentially generate harmful, biased, or inappropriate content if prompted maliciously. Careful usage and safeguards are needed. And crucially, code generated by LLMs, especially models trained on vast amounts of internet code, can sometimes inherit security vulnerabilities. You absolutely need human oversight, code reviews, and testing in secure environments before deploying AI-generated code in production. It's a tool, not a magic wand.
Okay, let's wrap this up. UICoder really feels like a significant leap, doesn't it? Enabling LLMs to generate high-quality UI code by essentially teaching themselves using this clever automated feedback loop. Taking an underperforming open model and making it rival the proprietary giants, all without needing massive human labeling efforts or getting tied up in restrictive licenses. That's pretty huge.
It really is. This deep dive, I think, highlights the incredible potential of letting an LLM learn through automated trial and error, guided by smart feedback, not just conceptually, but producing tangible, compilable code. This ability to automatically generate and refine training data for something as complex as UI development, it really opens up new possibilities for AI in specialized domains. It's a powerful new training paradigm.
So the final thought to leave you with, if LLMs can learn to master something as nuanced and frankly difficult as UI code generation, using these sophisticated automated feedback systems, what's next? What other complex domains, maybe ones we thought were purely human territory, intricate design, complex engineering problem solving, perhaps even aspects of scientific discovery, could AI learn to tackle autonomously using similar self-improvement methods? It really makes you wonder how fundamentally this could reshape the way we approach solving complex problems in the future.